In our next section, we'll talk about magnetic forces on moving charges. First, let's just do a throwback to Physics 1051. I guess most of you guys did Physics 1051 in person and you had to make a DC motor. If you didn't, you can certainly do this at home, and I can play a YouTube video that shows the making of the motor. You get some wire, and you can get all this stuff at Radio Shack anywhere. Just get a little bit of wire, make it into a coil, and sand off the ends. You have to sand them off because you want it to make an electric contact. You grab a power supply. In the lab, we used a DC power supply. You can just use a battery. And you set your coil in a couple of stands. We used paper clips in our labs. You have to make sure that they're not insulated. Then you connect the system to your battery so you get some current flow. You bring a battery nearby and it starts to spin. No, wait. I said you bring a battery nearby. You bring a magnet nearby and it starts to spin. You see that it matters which end of the magnet is facing it. So the direction of rotation is affected by the spin. And how fast it's spinning depends on how far away your magnet is or your magnetic field strength. So this was a super experiment that showed that there is a magnetic force on a current carrying wire, and that tells us that there must be magnetic forces on moving charges. That's what we're going to look at in this section. So there are some experimental observations about the magnetic force on moving charges. Experimentalists have discovered that the magnitude of the magnetic force, FB, it's proportional to the size of the charge, so it's proportional to Q. Bigger charges will feel bigger forces. It's proportional to the speed. Charges that are moving faster will feel bigger forces. And it's proportional to the strength of the magnetic field. If you put a charge in a bigger field, it's going to feel a bigger force. It's also dependent on, I won't say proportional to, but it's dependent on the angle alpha, where alpha is the angle between the velocity vector and the magnetic field vector. So lots of stuff affects the force. It depends on the charge, the velocity, the magnetic field, and the angle between the field and the velocity. So for the angular dependence, observations show that if the velocity and the magnetic field are parallel, then the magnetic force is zero. But if the velocity and the magnetic field are perpendicular, then the magnetic force is not zero. Okay, that's a very interesting result. Let's just think about that in terms of gravity for a moment. Let's imagine that gravity was like magnetic forces. That means if you stayed still, or your own personal velocity was zero, so here's you standing on the ground, not moving. If you were still, your velocity was zero, it would mean that your force due to gravity was zero. What would that mean? Well, you would float up in the air. So there would be no gravity to hold you down because you're not moving, and gravity doesn't exist if you're not moving. That's kind of interesting. Okay, what if you did decide to move, but you moved up? So let's say you just take a little jump in the air. Well, then your velocity is parallel to the gravitational field, and your gravitational force would still be zero. So gravity points down. If you tried to move up or down, there would still be no gravity, and you would just float upwards forever. Okay, so that's what would happen if gravity was like magnetic fields. And one last thing is, what if you took a step sideways? So you're standing on the ground and you take one step to the left. Well, what happens then is that your force due to gravity would not be zero and you would fall down. So gravity would turn on as soon as you took a step sideways. Then you would be flat on the ground. Okay, so to me, that's a pretty amazing result. I can't even fathom what our universe would be like if our gravitational field acted like magnetic fields. So I think the crux of what I'm getting at here is that magnetic forces are really strange and they're a bit weird to think about. Okay, what other experimental results do we have? If we make our charge Q negative, we find that the magnetic force is opposite to that of a positive charge. We can put all of that together to see that the magnetic force is the charge Q times the cross product of the velocity in the magnetic field. So if you're calculating a magnetic force, you can go ahead and do the cross product, or you can use your right-hand rule, remembering that the right-hand rule will apply to a positive charge. So you would find your magnitude, FB, is Q times V times sine alpha. And the right-hand rule says you point your thumb in the direction of V, your index finger goes with B, and your stuck-out middle finger would show you your force. We're going to do some practice on that. Let's do some practice examples. In this one, we have a positive charge. It's moving to the right with velocity V, and it's in a magnetic field that points up. Let's use our right-hand rule and find the direction of the magnetic force. So we point our thumb in the direction of V, we point our index finger in the direction of B, and our extended middle finger shows the direction of the magnetic force, straight out of the page or out of the screen. We represent that by a dot with a circle around it, and we label it FB. Now, if you prefer just to do a cross product, you would write FB equals QV cross B. Your direction of FB would be plus the direction of V, which is to the right, or I hat, crossed with the direction of B, which is up, or J hat. And then you might just remember your cross products, or you might do the little triangle like I do. As you go the right way around the circle, you get positive values. So I cross J is K, so this shows that the direction of our magnetic force is K. Either way is fine. You do whichever one makes the most sense to you. This one looks a lot like example 1, except this time we have a negative charge. So there's a negative charge right here. It's moving to the right in a magnetic field that points up. We still do our right-hand rule, but we'll account for the fact that it's a negative charge at the end. We start by pointing our thumb in the direction of V, extending our index finger in the direction of B, and our middle finger shows the direction of force on a positive charge. That's out of the screen. This is a negative charge, so we have to flip our result, and the direction of the magnetic force is into the page. We draw that with an X and a circle around it, and we label it FB. Again, you can do the cross product if you prefer. FB is QV cross B. This time our Q is negative, V is to the right, that's I hat, B is up, that's J hat. We've got negative I cross J is K, so it's minus K direction, or into the page. This example gets a little bit twisty. V is into the page, so your thumb points away from you into the page. Then you put your index finger in the direction of B. Might have to twist your hand a bit. Then your middle finger shows the direction of a magnetic force. That would be on a positive charge. This example is a negative charge, so we have to flip the force and it points down. So our magnetic force this time points down. You can back that up with the equation if you like. FB is QV cross B. The charge is negative. V is into the page. That's a negative K hat direction. It's crossed with B. That's to the left, a negative X direction. So minus K cross minus I is K cross I. And K cross I equals J. So the direction of the magnetic force is minus J, or down. Here's what some people might call a trick example. V points up and B points up. So you try and get your right-hand rule. There's V that points up. Then you have to extend your index finger and also make that point up. That doesn't actually work out. So here you have to remember that when you have a cross product between two parallel vectors, that answer is 0. So we remember the experimental observation. When V and B are parallel, the magnetic force equals 0. So for this guy, there is no magnetic force at all. This last one has V and B not at a 90-degree angle, so our V is partly to the right and partly up, kind of like this. So we make our thumb go with V, our finger go with B, and our extended middle finger shows our magnetic force. In this case, the magnetic force comes out of the page. So we'll draw that force. Then if you wanted to do this with the equation, FB is QV cross B. The charge is positive. V here has an I part and a J part. You have to think about both parts. Cross it with the magnetic field. The magnetic field points straight up, so that's the J direction. Then we do our distributive property. We've got I cross J plus J cross J. I cross J is K, and J cross J is 0. So the direction of the magnetic force using the equation also gives K hat or out of the page.